Me?
Yes. Hi, Jonathan.
Hi, Sasha. Sorry, a little mix up
Now,
there.
I think there was a problem from our side. The Zoom link wasn't sent through to the calendar of people, and
Okay.
we sent it just 10 minutes ago, but I don't think you have registered for your own talk, so that's why you didn't get it.
Oh, my
Um,
apologies.
no, that's all good. So I'll just
Yeah.
quickly do the acknowledgement of the country. Let me just introduce myself to people. I think we have 30 people online. I'm Sasha. I'm Senior Geophysicist in Geological Survey of Queensland, and I'm the Chair of Professional Development Committee in ASEG FedEx. And this is our very first seminar that we have decided to do this year. Um, Jonathan has accepted to be our first speaker, which I'm very grateful to Jonathan and the company. Um, so I'll read the acknowledgement of the country. The ASEG acknowledges the traditional owners of the land on which we gather today and the many lands on which we undertake our work. We recognize the continuing connection to these lands, water, and culture, and pay our respects to elders past, present, and emerging. Um, also, this is our first seminar. It's recorded, so you guys can go back to it. And the second one will be in a month. Will be done by Anand from GA on basics of inversion. And after that, we have another seminar that we show some IP data modeling and processing. But before Jonathan starts, I give an introduction. Um, he got his geological engineering, geophysics degree from Queen's University, Canada, and he worked in several ground and airborne geophysical contracting groups and also Geological Survey of Ontario for a couple of years. And he's a founder of the DIAS Geophysical and has been instrumental in its growth over the last 12 years. And yeah, now to you, Jonathan, please.
Okay. 1 second, I'll just share my screen. Okay. Can people see that? Okay.
I only see you so far. I don't know what other. Oh, okay, now it's good.
Okay.
Yeah.
So I'm not sure if you wanted to speak to these slides, Sasha, or whether I should just proceed.
I think you can proceed. That's fine. Um,
No,
that's okay.
our corporate
Yeah.
members.
I think we are a bit behind, but
Yeah.
yeah,
Okay.
yeah.
Upcoming events. So I'll move on. So yeah, thank you for the introduction and for this opportunity to speak. I'll move into this presentation right away. We're talking today about the DS32 IP system, which has been around for about 10 years in commercial production now. And as mentioned, I'm Jonathan Rudd with DS Geophysical, and GAP Geophysics is a subsidiary of ours in Australia. So just a brief outline, going to make some brief comments on 3D DCIP, describe the system, and then describe its features, and then get on to some case studies. So I'd like to start with this slide. This is kind of a look over to the seismic industry and the time when the seismic industry went from 2D to 3D.
Mm.
And we're in that, still in that phase, I think, with the transition from 2D IP to 3D IP.
Mm.
The chart on the top right is really the telling one. Between 1990 and 1996, we see that these dry holes, which it was all 2D, so the top two portions of the graph there are 2D surveys, and the bottom two are with 3D. And you can see that about a 10-to-1 ratio of dry holes to producers before 3D was introduced, and by the time 3D came into full use, it was about a 50-50 when using 3D seismic. So this is kind of where we think the value in running to 3D surveying in general, and obviously today I'm speaking about 3D IP, but we believe that we'll see similar improvements to drill success as a result of 3D IP. So what is it? How do we define what 3D IP is? This is just a 2D section showing, current pathways, energizing a chargeable source, and then the currents that are flowing out of that source on discharge, and then the voltages that are measured at surface. In a conventional 2D survey, in the top right here, you can see an current injection point here, and I'll call it a pole dipole array. And a conventional 2D just has receivers on one side. A distributed array 2D survey, like MIMDAS or Titan, would have receivers on both sides of the current injection point, advantage in that. But a full 3D survey really is occupying the survey area in all directions around the current injection points. That's the ideal, what I would call a full 3D. Most 3D surveys now really are partial because it'd be too expensive to do a full 3D survey in every case. So you often get these sort of skewed or biased or what I call partial 3D surveys. So it's important to understand that each 3D survey is a little bit different in its content. So looking at some partial surveys, so White way back in the 90s was talking about this offset 2D approach, where you're getting some 3D information in the shallow portion of the survey area because you've got some angles, going to the right here and sort of offline. But really, as you go to depth, mid-level depths and deeper depths, this really is a 2D survey. And similar to what one contractor here in Canada does as well, maybe a little bit better in the near surface because you've got a little bit more. These green points are the dipoles, receiver dipoles, and you see a little bit more 3D in the shallow near surface. But really, as you get to depth, your long offset information is really just 2D. So I would characterize these as either offset 2D or partial 3D surveys. When you get into a survey where you're occupying the whole or a large portion of the survey area, in this case, so the green dots are receivers and the red dots are injection points. You can then look at a true sort of a 3D space. This is 0 to 70 meters, the top left one, and then 70 to 140, and then at depth you start to see the fact that it's a square survey area. So that's kind of a brief discussion of the 3D IP space. We do recommend that you understand what you're getting when you're considering a 3D IP survey. So I'm going to get on to the system description. This is our system, the DIAS32 system. It comprises a single channel set of single channel receivers. Here's a box of 25, a couple boxes of 25. Each one has a GPS in it, storage for the time series data, a network radio, and a long life battery. The battery's 5 or 6 days. Relatively small, so it kind of fits in your hand, lightweight and fairly rugged. The other piece of the equipment is the transmitter. Our GS5000 transmitter is a relatively high power unit, 25 kilowatts, and high voltage. So the combination of high current, high power and high voltage is unique out there. It produces up to 20 amps and is quite portable. You can put it in the check bags at 32 kilograms. So these features of the transmitter are helpful, obviously, from an operational standpoint. We don't have to open it up, so very safe. Everything's controlled remotely. And lots of other flexibility by having 2 power inputs, so we can use 2 generators if we want. We can go with the DC or 3-phase or a single phase generator. So this combination does provide a high signal to noise output, and but the core of the DIAS32 system is what we call common voltage referencing, or CVR. And this is just a 2D sort of depiction of what that means. What we're doing is we're taking a receiver, single channel receiver, at each electrode, and we're measuring the voltage between that electrode and a common voltage reference wire, which is the red wire that comes out here. Now that wire has to be, we need to bootstrap it down, so we ground it at some reasonable distance outside the survey area. And then we're measuring the voltage really between the local electrode and that grounding point off to the side of the survey area. But because we're measuring time series, that allows us to then subtract any two of those measurements, whether it's a small dipole or a large dipole. The advantage of that is that it provides depth sensitivity, high resolution, low noise, and it provides operational efficiencies. And I'll get into these in more detail in further slides. So this is a 3D depiction. So here's what we would commonly do in a 3D survey. We would lay out several lines of receivers. And then that allows us to calculate not only inline dipoles, but also cross-line dipoles. Sorry, it's a little bit jumpy here. Apologize for that. So, and it means that for every pair of active receivers on this array, we can calculate a dipole. So here you can probably calculate hundreds of dipoles through combinations, the various combinations that are available here. And they're all grounded to this common voltage reference. So the red wire that's shown here. So this is just a depiction of the dipoles that can be computed for a relatively small number of receivers. Typically, our 3D surveys are producing about 100 times the data volume compared with other 3D IP systems. And you can calculate the number of potential data using that formula on the bottom there. And so if we have 300 or 400 receivers out that are active, you can see how the data volume ramps up very rapidly. And perhaps the feature here is that you're not just getting a long line dipoles, you're getting a cross line dipoles, and you see how the resolution really does improve as a result of this. So this is a processing output. So we have two electrode responses, the green in the top panel and the pink. And if we take those two and we want to create a dipole, we just subtract those time series. And the resultant is the black. So that's a dipole response. You can see there's some EM coupling response in there, but you can see that the long wavelength noise that's present in that common voltage wire is subtracted out. So you get a very, very clean dipole response every time. And then this is an example of just a single half cycle. So an on and an off cycle. And you can see there's high frequency noise in each of these two individual dipole responses. And that high frequency noise could be anything. It could be transmitter. It could be something that's being induced in the reference wire. But again, even the high frequency noise gets canceled out. So the resultant is very, very clean data. And this sort of low noise character is independent of how far apart the dipoles are, because that common reference, the common mode noise in the reference wire gets subtracted out. So operational considerations, we also have batteries that are long life. We have a cable-free mesh networking system that is integrated into the receivers. And all these things bring operational benefits. So the common voltage referencing and the batteries mean that you have really less wire to deploy on a survey because it's just a single voltage wire along the line. And that also means you have less walking, less weight, so less wear and tear on your field personnel. And the cable-free mesh networking, which is XB seismic technology, tried and tested, provides a host of advantages because it gives us great visibility on what's going on in the receivers and through the survey area. So we can monitor crew, we can look at real-time results, make real-time decisions, and monitor operations, knowing how fast or slow things are going in different portions of the survey area. So we can look for wire integrity, whether you've got a cattle or anything else that have interrupted some of the connections. You know that right away and can go and address it. So this is an example of a survey where we had a couple hundred, I think it's 170 receivers out. And the operator is able to log the information from those receivers and determine what, whether there's any problem. This one is colored based on VP. So you can see if there's any potential, outliers that need to be addressed. We can identify current leakage, again, using that voltage characteristic. This is a large survey area and about 25 square kilometers, and we're able to log each of those receivers and find that there's the current wire is actually running along this line here. And we can monitor where the voltages are not behaving as we might expect, not falling off normally. So we're able to identify current leakage. I'm going to move on to data analytics, and then I'll try to step through this fairly quickly so we can get to some data. Just a few key takeaways from working with large data sets. You really do have to prioritize quality control before you get to the signal processing stage. So that's in the field. Time series and location data, we have to do that in the field. So we must verify that fundamental data quality and completeness real time, which is what the XV allows us to do. Automation must be a part of the solution, and you'll see how we're doing that in the slides to come. So we have real-time equipment health, as I've mentioned already. Time series quality control. We do daily background measurements, and you can see how we're able to monitor the receivers and then pull the information that we need at any given time. If we suspect there's a node that's bringing in bad data, or for whatever reason, we can pull it and pull the data back. So across the bottom here is a live time series record that the operator can assess and try to determine what the problem might be. Our advanced signal processing is done in the office. We pull nodes back to get the data to the office, and we'll get into what's done in the office next. So we use a convolutional neural network-based time series analysis for the initial analysis of the time series data. And we've got a number of parameters that we test against, whether it's a good edge of the waveform, can we identify the edge of the waveform, and are there EM spikes, is there a time shift problem? And so all of these things are done in an automated fashion. And of course, with any CNN or machine learning method, you want to verify the output, make sure the decisions are valid. And so we can step into identified dipoles, pull up the time series, to do a power spectrum analysis, and then you can see what the machine learning, the neural network is telling you might be the problem. There's just a couple examples of that. So very, very user-friendly. You can click on any dipole or any pole and try and source the problem. So the processing stage, after the CNN is complete and checked, we do a pre-stack, looking for noise sources, identify outliers, and we quarantine them. Do dipole selection, typically n of 1 to 10. And we choose a dipole azimuth range, and then we identify and call poorly coupled dipoles. Post subtraction, pre-stack noise, identification removal, and then stacking. And we have several methods for stacking. So this is an example of how in one data set the dipoles were being built. We do use a point cloud, so this is kind of the 3D analog to pseudosections. And the point cloud is useful for visually identifying major inconsistencies. So it still is a tool that can be used to identify outliers. It is part of our process. We use for IP. We have good decay analysis, and we adjust our integration window to try and minimize our noise. And we use a coal fit as well to try and understand what best integration window is going to be, particularly in areas where we know there's EM coupling effects there. So this analysis is done prior to finalizing the window and producing the chargeability data set. And we use inversion as a final QC tool. We can use the residuals to identify any remaining outliers. I'm going to move on because I'm running out of time. I have a fair bit of stuff to get through here. But we do produce an inversion as a product, an initial product, unconstrained inversion. And so it makes sense that we look at the data and how it performs in those inversions. So large 3D data sets, they're typically 100 to 400 current injections, 100,000 to 1 million observations. 10 kilometers squared is pretty typical. And we work in a lot of different challenging terrain. So elevation gradients are common. And what types of inversion codes we use? Generally, we use the SIMPEG tensor mesh code. And then we use what we call tiling, which is a development that DIAS completed. It's breaking down your data set into smaller chunks, which speeds up the process. But Voxy can run our data sets, Res3D Roke's code and UVC code can all run our data sets. It took us some time to get them to be able to handle the high volumes that we produce. So tiling, as I mentioned, is a method that we use relatively commonly for our higher volume data sets. It's simply taking a portion of the data. In this case, you're taking it by current injection and all the active receivers that are associated with them. And so you might break it down to 7 or 8 tiles, and then you concatenate them together. And then different ways of doing that, but it improves our inversion times by a factor of about 3 to 4. This is what our experience is. I'm going to move on. We get on to system features, and then we'll get into some use cases here. So as mentioned, the system is very scalable and flexible. You can go from a very, very small, tightly spaced survey all the way out to a very, very widely spaced survey. In this particular case, this is a 500 meter by 500 meter survey block, and then we followed it up with a 50 meter by 50 meter survey block to characterize aquifers and hydraulic connectivity in this tailings management application. And the detail block was done just as a test to understand how there was calibration over an existing borehole to understand how the data matched that. And we'll move through this. So we were able to identify the upper aquifer and the lower aquifer. The lower aquifer was the one of interest. And so they can isolate that lower aquifer using a series of parameters, resistivity and depth. And then we can analyze that layer. We can see that there is a graben structure, which they knew ran through that survey area, which is actually changing the character of the aquifer on either side of it. It's thinner and less certain on the one side and thicker and more certain on the other side of that graben structure. This survey was only looking down about 120 to 150 meters by design. This is an example of a large-scale porphyry survey we did in the Andes. So this is a different scale. Each of those green dots is a receiver, and that receiver spacing is 500 meters. And the current injections are red, and they're 1.5 kilometers. So a total area of about 50 square kilometers. And this survey was feasible even in rugged terrain with the Andes. It was important they wanted a good 3D model for a clear interpretation to move their project along more rapidly. Take another look at mountainous sort of applications. This is typical in Western Canadian environment, to the Western US and of course down in South America. I'm going to skip this one, other than to say that, I can get the video going. Other than to say that this was a custom layout. It shows the flexibility, really rugged terrain. We put our receivers out along the ridges of the survey area. And it doesn't look like the video is working very well. But we put our receivers out along the ridges of the receiver area, of the survey area, and the crest and the ridges as sort of a custom layout like that. And then we did our current injections around where we could. And we produced quite a good 3D data set from this in a relatively rapid fashion. About 10 days to complete this survey. I'm going to skip this example, other than the first couple slides, because this shows an example where we can sort of do a dual resolution survey. So here we have a few lines of extra receivers sitting in an area where they have known mineralization. And then we did our survey. The current injection line is the red, and then the black box is the active receivers. And we can just move that along to get fully across the survey area. And you can see the data set that came out of this. This is millions of data points as a result. And I'll just quickly show you the final chargeability data set here with the additional detail through their area of interest. And then the resistivity data set here, showing lots of good structure and detail through their area of interest. Obviously some silicification through there. We go to depth. So resolution, I've kind of covered this already. This is just the advantage of having those interline dipoles, not just the long-line dipoles. And we did a little sort of a test of a survey that we completed. We stripped out all the interline dipoles. We just used the inline dipoles and ran the inversion. And on the left, you can see that is the one where we're not using the interline dipoles, so just a long line dipoles. And on the right, we're actually using the full data set, so to see all the CVR additional dipoles. And you can see that the interpretation from the inversion is really quite remarkably different. And we would plan drilling or understand the geology in a quite a different way based on that additional information. It's another example from the western US, a relatively rugged terrain. The yellow and red block here is a relatively conductive intrusion, weathered intrusion, and then got all these fingers coming off that intrusion, and the ability to image those individual features with relatively high definition, even if they do run sort of parallel or sub-parallel to the survey lines, which are running along here from the top right to the bottom left. And likewise, the chargeability in the dark green here, or the green, is showing you good detail. Another example of resolution here, we're imaging epithermal gold target veins, and they knew about this east-west sort of fabric, but they didn't know about this northeast fabric. And so we imaged some pretty interesting directional information for them using the 3D technology. Here's comparing a quick one to compare an old survey that was done at the same line spacing and same station spacing to the DIAS32 survey. And in the top right is that comparison. So there's a line here which separates the old on the right to the new to the DIAS survey on the left. And on the right is a 3D survey. It's just a different variety. And on the left is the DIAS32 survey with the full CBR benefit. And again, same line spacing and station spacing, just different methodology. So quite a stark difference there. It's helpful for them to understand where their goal horizons are likely to be targeted. Sasha, can I ask what time I should end up here before questions?
Sure. I think you have another 5 minutes, but you can have another 5 minutes maybe after that. We leave 10 minutes for questions, so you have 10 minutes.
Okay, sure.
Since we start a bit later, I guess. Yeah.
Sure. Okay, we'll see how patient people are, I guess. Yeah, so this is a final sort of a view at resolution of the system, and what is it in the system that determines the resolution of a survey. And this is just a porphyry model, chargeability with a cap and a stalk, I guess. And then this is the resistivity on the left. So fairly typical vertical cylinder sort of porphyry model. You can see the details of each of them there, relatively basic. And all we did was we wanted to understand what the effect of changing the receiver spacing and the transmitter spacing was on the resolution of the survey. So we've done some depth slices here from 50 meters across the top, 350 meters depth, which is, it's down 300 meters, so you expect it to pick up at about 300, and then deeper at 650 meters. And across the columns are basically we're stripping away current injection points, and we can see that we're stripping them away actually quite, to an order of 10 to 1 almost, or 1 to 10. And we can see that the resolution is not really falling off with that removal of additional transfer points. And so that's been our experience, is that the resolution of a survey is really determined by your receiver spacing, and not so much by your current ejection spacing. So we've actually modified our recommendations for surveys by using this information. Same with chargeability. No significant loss of resolution by decreasing the number of current injection points. And then the other one is depth resolution. This is just a small synthetic study where we're looking at two sources, conductive sources in a relatively resistive background. Here we're just using sort of end-to-end dipoles, 300-meter dipoles, and inverting it. You can see that it's noisy in the near surface. It kind of sees your two sources. But if you take and tighten up your spacing, your dipole spacing, to 100 meters, which is the top left here, you can see it's really doing a good job at sort of limiting your near surface noise and locking in that top edge. But it's not doing a very good job at depth. Now, if you take a 300-meter dipole and you move that 300-meter dipole along at 100-meter intervals, so you're overlapping your dipole, you're not doing as good a job in the near surface, but you're doing a little bit better, in defining the bottom edges of those things. But now, if you take both, you do both 100 meters and 300-meter dipoles, which is what a CVR system provides, you can see it's pegging that top edge pretty well, and it's also doing a pretty good job at depth. And so the CVR methodology really does help with sort of both near surface and detail at depth. So what are the depth search factors? Obviously, signal, powerful transmitter, noise. The common voltage referencing gives you a low noise output. Having larger dipoles is important, and then high resolution. If your geology is complex, you got to figure out what's going on in the near surface to really be able to resolve what's going on at depth. So you can't resolve what's going on in the near surface. It can contaminate what your model is telling you about your deeper sources. So we believe the value of that there is value in that high resolution in the near surface. And then having lots of data in noisy environments gives you a little more flexibility for processing and culling of that noise out. So this is just a depiction of the advantage of a large receiver dipole. Small receiver dipole gives you, some depth, long ways away, but really a large receiver dipole a long ways away gives you much better depth search. And so that's one of the big advantages that we have. I'm going to move on here. I'm going to move on past this one as well. Sorry about that. We'll get into a couple of use cases here. So this is a survey we did in South Australia for Alliance Resources. We've done a gold deposit, about a 50 to 60 meter cover, pretty conductive cover. So having the high powered transmitter was important. And we were able to see the color in the background here is chargeability. We have some known mineralization, which is given in the cyan colors here. And then some new targeting done by Southern Geoscience using our data sets. This is just an oblique view of that, looking down towards the north there. And some new chargeability that was not well understood off in this sort of northwest limb of this feature. Looking at the higher grade gold shoots and how they relate to the chargeability, not a real direct correlation, but there is certainly an association. And so they were sorting that out. And this is looking up from underground at that model. See the one limb and this new limb, and they're quite interested in this highly chargeable source here to the northwest, which hadn't been really explored at all. I'm going to do one more, and then we'll call it a wrap. So this is a relatively a couple of years ago we did a survey for Hercules metals, and it's a discovery of a porphyry system in Idaho, which is a not porphyry hunting ground to date, but things I think they're changing. We did a 3D survey back in 2022. You see the lines here in the left side of this image. And they were really looking at these near-surface silver, lead, zinc thermal deposits in the top couple hundred meters. And so they did image those quite well with the survey. And you can see some new potential zones up to the north here. But they also were quite enamored by this large chargeable source at depth. It's about a 200 meter depth. They looked back at their drill holes, found that there was some increasing mineralization at the bottom of their holes, and so they plunked a hole into it, and they hit 185 meters of 0.84% copper at that 200 meter depth. So that was the discovery hole for this deposit. And they continued on using this data set for their exploration. We went in the following year and expanded it, and to a larger area, and they're using that as a key piece of their modeling and interpretation workflow. So, in the interest of time, I'm going to say that that's all. So I appreciate your attention, and I'm happy to take any questions you might have.
Thanks, Jonathan. Anybody have a question in the audience? I don't see any hands. Do I? Nah. Thanks, Jonathan. That was a very interesting talk. Oh, babe, Jack.
Hi, thanks.
Sure, Jack, go ahead.
Sorry, I was trying to still find the hands button.
Yeah.
I was interested to know a little bit more about the compute details for the tiled inversion, how you stitch the tiles back together after the fact, and any strategies for doing that, because I know that can often cause stitching artifacts if you try to domain inversions.
Yeah, you know, I'd probably put you in touch with John Cutai, who's at the UBC, or Charlotte, our data analytics person. I know it is a fairly simple process to put them together, and we've compared that with a with a non-tiled survey, and we've got some sort of excellent sort of results. No sort of relics of that stitching.
I think
So
it's a 1D problem, isn't it? It's not that bad if it's with IP and DC resistivity. I guess Jack's
yeah,
background is seismic.
right.
Yeah.
If you decide to do that with seismic, I'm sure you see a lot of crappy stuff. But
Yeah,
the
definitely.
1D problem wouldn't be so horrible with stitching.
Okay. Thanks.
Anybody else? Any questions?
Yeah, Jonathan, quick one for me. Just wonders, is there any comments around the significance of the location of the remote electrode in surveys, and if you've used with that, or things you try and consider when looking to place that remote electrode?
Yeah, we are we are careful with that. We try to keep it on more resistive ground if we have that option. Certainly, we don't put it far enough away to call it an infinite. We call it a remote, and we include it in the inversion at all times. Yeah, we try to go perpendicular to the survey lines to minimize any sort of coupling with receiver wires, and we but often the operations, like the access, road access, and all of that is a pretty big factor in all of that as well. So yeah, I don't think we're doing anything um, unduly remarkable in that regard, but we are following a lot of the best practices in the industry for that.
Okay, thanks.
One slide I did want to, maybe I can just talk about it because there's not a lot of videos on it, but I did want to kind of give an update on where we're going with the system development. So we just introduced a Gen 2 system, so it's a new updated receiver, which has got a better onboard processing, real-time QC, enhanced real-time QC, a better GPS, and better storage. So just kind of a souped up version. We're really working towards having near real-time inversion from coming out of our surveys. So by the end of the day, you'll have enough data back to be able to run an inversion to see where things are going, if there's any modifications to the survey design that would make sense for the client, and obviously identifying potential problems. So that's the real-time inversion is a work in progress, but we now have the hardware and the sort of platform on which to develop it. And we are building a higher powered transmitter as well. And that transmitter has been tested. We've had initial field tests for it. It's 250 kilowatt and 12,000 volts, and so fairly capable machine. And we're looking forward to the benefits that brings. Brings obviously depth benefit, but it also allows you to survey a larger aerial area, right? Energizing more ground laterally as well, so more efficiency in terms of covering your ground. So depth and survey coverage, two birds with one stone, as it were. And yeah, that's the update on sort of where the our development is going with the system.
Right. Januka, it seems, has a question.
Muted.
Januka, you're muted. We cannot hear you.
Sorry,
Okay.
I'm trying to switch on my camera as well.
Yes. We are supposed to be all technology savvy as geophysicists, but still, I don't know. With Zoom is always a problem.
Use Zoom. I'm typically using Teams, so
Yes.
Yeah.
Okay, sorry, my camera is not working. Sorry. Jonathan, that was a very interesting presentation. Thanks very much for what you just showed us. I have a question about electrode coupling because electrode coupling can be a pain in the neck when you're doing IP. And that is even more so when you're trying to increase your power, right? The current injected into the ground, which I guess you're trying as for the development of the system. And looking at your signals, they look crisp to me. The few signals that you showed us. How do you overcome electrocoupling in your processing flow, or is it something to do with the hardware itself?
So are you referring to EM coupling? So the coupling of
correct? Yes.
Yeah. So it's present in our data as I think anybody could imagine, and James's question around placement of remote is important in terms of minimizing the EM coupling. We use sort of conventional approach of moving later in time in the decay to minimize the effect of that EM coupling, as long as it doesn't extend too far into the decay. So we'll move our window out, 400, 500, 600, or even later than that. We can move to a lower base frequency as well, to allow us to avoid EM coupling in the early time if it is pervasive. And then we get a lot of data. We get millions and millions of data points in some of these surveys, and so we have the ability to call the EM coupled compromised data, and still have a robust data set with which to interpret and image. So does that answer your question, Jonathan?
Yeah, I think so. The question I have is that we are applying these methods at the engineering site scale, so we don't have millions of data. So we have to do very manual type of data processing.
Yes, we've done a few of these surveys in engineering applications, void detection, groundwater sort of mapping, both shallow and deep. And you don't see the EM coupling effects as much in the resistivity data set, which I suspect the data set that you're primarily using. More of that effect is seen in the chargeability and the decay portion of the
One other quick question I have, Jonathan. Are you working as a consultant, or is the system available out in the market?
So DS Geophysical owns this system, and we run surveys ourselves. So we're a service provider.
Okay.
And so, but we do processing and inversion. We think we sort of feel our data acquisition is our sweet spot. That's our core competency, and we leave the inversion and interpretation and integration to groups that are set up for that. But we do provide initial modeling, again, primarily to verify the data set, but it also provides a valuable first look for our clients.
Yep, fantastic. Thanks a lot.
You're welcome.
Okay, I think time is up. I'm going to ask the last question myself. Have you done any large scale surveys, like type of regional ones that government like to do?
Yeah, so we've done the one that I mentioned there was about 50 square kilometer. We've done a couple hundred square kilometers surveys in Saudi Arabia. We've done some fairly large scale surveys in the Western US as well. One of them is actually about a 30 square kilometer survey for groundwater. Regional, I guess the closest we came to a regional style survey would have been that the one that I showed in the Andes, where we used a 500-meter dipole spacing.
Yeah.
That approach is probably most amenable to.
Yeah.
Might call it regional exploration.
Yeah. All right. Thanks very much, Jonathan. That was amazing. I definitely enjoyed and hope to see you work more in Australia, especially with your new, transmitter high power. We have a lot of cover in Queensland.
Yeah.
That probably can show something. Yeah, that was fabulous. I have a lot of questions, but there's not much time, but definitely enjoyed.
If
And
anybody
yeah.
want to share my email, feel free to
Yes.
share my email for anybody that might have any further questions.
Absolutely. Yes, I will do that. And this is recorded so everybody can watch it online. We're going to put it somewhere, I'm sure, for people to see it. And yes, thanks so much again. Our next seminar will be I guess in a month. And the next person to talk is Anand Ray from GA, that he will talk about basics of inversions, and then we will have some real IP data to show to people for processing and modeling. But yeah, I don't know who's going to do that one now, but I will put it online. We'll post it. And yeah, thanks everybody for joining
Thank you
us.
so
That
much
was
for
great. We
organizing it.
have quite a lot of people. Yeah.
Mhm.
Yeah, no worries. Thanks everyone. Have a great day.
Thank you. Thanks, Sasha.
See ya. Bye.
Goodbye.